Hi, everyone, and welcome to another LIC class. So in the previous class, we finished the low pass filter, high pass filter, higher order low pass and high pass filter. We went through band pass filter as well, a little bit, explained about that. Today, we want to continue the band pass filter, and also hopefully we can finish band pass filter and the characteristics of a band pass filter. So we know that a band pass filter is a combination of a low pass filter and a high pass filter. When designing a band pass filter, we have to take into consideration our frequency response and the frequency response of each filter. Meaning, we have to design a filter in a way that the low cutoff frequency and high cutoff frequency are far enough from each other to create an adequate band pass frequency or frequency response. So for example, if I create a low pass high pass filter, if I create a high pass filter which looks like this, and my low pass filter looks like this, if I combine these two, then I would have nothing left and everything would be filtered out. So, and imagine that both of them have, this one has a cutoff frequency of 1 kilohertz, this one has a cutoff frequency of 1.2 kilohertz. So designing the system, we have to be sure that these two are far enough, and that depends on our design. Sometimes we need a very narrow bandpass filter, sometimes we need a very wide bandpass filter. Interesting enough, we have an application for this filter as well. This is actually called a notch filter. So if we add a low pass filter with a high pass filter like this, so this is the LPF and this is the high HPF or high pass filter. We have created a zone which is called a stop band or the stop zone. And this is actually what we call the notch filter or a band stop filter. This is called a band stop filter. So band stop filter is the opposite of a band pass filter, okay? We want to pass every other frequency, we want to pass every other frequency, but block a certain frequency, okay? Which here, for example, could be between 2 kilohertz, for example, and 3 kilohertz. Now, what do you think would be an application of a stop band filter or a notch filter? A stop filter. What do you think would be a good application for this?
You could put in kind of speaker system the 60 hertz.
Perfect. Great. Yes, you can put it in a speaker and block what we call the humming noise, or a 60 hertz that we have. Another application is that imagine you're on an airplane, you're using an active headphone with an active filter, and that filter could filter out the engine noise from the airplane. So you're going to hear every other sound, but you're not going to hear the engine noise. A lot of applications actually for this. There's a lot of applications for this, especially in communication systems, when you want to block noise in a certain frequency. It's very good when you have a certain frequency, a fixed frequency, not a variable frequency. This is not going to work well with that. So for example, for these power outlets, we know that the frequency is fixed at 60 hertz. So you can just put a block filter or band stop filter at 60 hertz, and it's going to block everything that it's around, for example, between 58 and 62 hertz. So there's a lot of application, especially for noise canceling. So for a band pass filter, if the cutoff frequencies are, for example, FL is 200 hertz and FH is 600 hertz, then our bandwidth would be 600 minus 200, obviously, it's going to be 400. So imagine the lower cutoff frequency, this is 200, and this is 600. And our passband or the frequency response, this would be 400 hertz. So in this particular case, the frequency response and the phase shift would look like this. So we're gonna have a frequency response between 200 and 600 hertz. So the bandwidth for this one would be 400 hertz. And we're gonna have a phase shift in the middle of this band. So the frequency goes from plus 90 to 0 to negative 90. So you can see that in a higher frequencies, we usually have a phase shift, which is like the maximum around FH, that phase shift is around 90 hertz. How do we calculate phase shift? We use this equation that we had here. Phase shift is going to be tan inverse of 1 over 2 pi f RC. If we can write this down, because you're going to have another example from this as well. Did you write it down? Okay, perfect. So while the above passive tuned filter circuit will work as a bandpass filter, the pass band can be quite wide, and this may be a problem if we want to isolate a small band of frequencies. Active bandpass filter can also be made using inverting operating amplifiers. The only difference between an inverting and a non-inverting is that in a non-inverting amplifier, the gain would be negative R2 over R1. But the cutoff frequencies, the upper cutoff frequency and the lower cutoff frequency would remain the same. So for this particular case, if we have an inverting active bandpass filter, first of all, we're going to have two sets of capacitors, resistors, C1 and C2. Can you tell me which one is the high pass filter one and which one is the low pass filter? Which capacitor is the high pass filter and which capacitor is the low pass? Low pass meaning it passes even DC signal. Which one of these can pass? Which one of these actually blocks a DC signal? C1, perfect. So C1 is our high pass filter and C2 is used as our low pass filter, okay? So that's the reason if C1 is going to be 1 over 2 pi R1 C1, if C2 is 1 over 2 pi R2 C2. And I want you to write this down. We're going to use it for our next example. So sometimes we can have multiple feedback bandpass active filters. We can improve the bandpass response of the above circuit by rearranging the components again to produce an infinite gain multiple feedback or IGMF bandpass filter. This type of active bandpass design produces a tuned circuit based around a negative feedback active filter, giving it a high Q factor up to 25. Amplitude response and steep roll-off on either side of its center frequency. Because the frequency response of the circuit is similar to the resonance circuit, this center frequency is referred to as the resonant frequency or FR considered in the circuit below. So we can have multiple feedback active filters or what we call the IGMF. In this particular case, the C2 is connected before C1. So in the previous one, we saw that C2 and R2 are in parallel. Now C2 is parallel with R2 and C1. For a multiple feedback, F1 would be 1 over 2 pi square root of R1, C1, C2. And Q factor is going to be FR. FR is the resonance frequency or the bandwidth, or half of square root of R2 over R1. The maximum gain is going to be negative R2 over 2R1, or negative 2Q squared. We can see that the relationship between resistors R1 and R2 determine the bandpass Q factor at the frequency at which the maximum amplitude occurs. The gain of the circuit will be equal to negative 2Q squared. Then as the gain increases, so does the selectivity. In other words, high gain, high selectivity. Just give me 1 second. So first example, we have an active bandpass filter that has a voltage gain of 1 and a resonant frequency FR of 1 kilohertz. The FR is constructed using an infinite gain multiple feedback filter, or IMFG. Calculate the value of the components required to implement the circuit. I'll give you again 5 minutes. Did anyone find the answer for this? Oh. Does anyone have the answer? So for an active filter, we have to first determine the value of the two resistors, R1 and R2. The gain AV is 1, so negative 2Q squared is going to be equal to 1. In other words, Q is going to be 0.707. So when Q is 0.707, that's going to be equal to half of R2 over R1, square root of R2 or R over R1. Again, we're using this equation, and Q is equal to half of square root of R2 over R1. And that's going to be R2 over R1, which is going to be 0.707 over half in the power of 2. Therefore, Q is going to be equal to 2. Now, we can see the value of Q is 0.707 gives a relationship of resistors R2 being twice the value of R1. Therefore, we could put R1 as 1K, R2 as 2K, or R1 as 10, and R2 as 20, or R1 as 100, R2 as 200, depends on what we want to pick. The center or resonant frequency is given as 1 kilohertz. Using the new resistor values obtained, we can determine the value of the capacitor requirement, assuming that C is equal to C1, it's equal to C2. So FR is going to be 100 hertz or 1000 hertz, which is 1 over 2 pi C square root of R1, R2. It's going to be 1 over 2 pi times R1, F assuming 1000, and R1 and R2 assuming 10,000 and 20,000, gives us a C of 11.2 nanofarad. Yes. You write it down. Can I go to the next one? This is the next. Okay. So resonant frequency point, the actual shape of the frequency response curve for any passive or active bandpass filter will depend upon the characteristics of the filter circuit, with the curve above being defined as an ideal bandpass response. An active bandpass filter is a second order type filter because it has two reactive components or two capacitors within the circuit. As a result of these two reactive components, the filter will have a peak response or resonant frequency at its center frequency. And at that center frequency, which is again mentioned here, we're going to have F center, we're going to have a shift in the frequency as a shift in the phase as well. Phase is going to go to 0. And we want to, this is the center frequency is an important subject for us. And the way that we want to determine this center frequency, we can use this equation. FR is going to be FL FH square root of FL times FH. Lower frequency times the higher frequency. So the center frequency is generally calculated as being the geometric mean of the two -3 dB frequencies between the upper and the lower cutoff points, with the resonant frequency or point of oscillation being given as follows. Now, gain for an active high-pass filter, the gain for an active high-pass filter looks like this. The voltage gain AV would be equal to V out over Vn, which is equal to AF F over FC over square root of 1 plus F over FC squared. AF, again, it's the passband gain or the maximum gain of the filter. For a non-inverting filter, it's 1 plus R2 over R1. For an inverting filter, it's going to be equal to negative R2 over R1, depending what amplifier we use. F is the frequency of the input signal in hertz. and FC is the cutoff frequency in hertz. Let's solve an example. We want to calculate the gain of a bandpass filter when AF is equal to 20, F, the frequency is equal to 50, or let me get 500 kilohertz. And FC, the cutoff frequency, is 200 kilohertz. What is the gain or AV going to be equal to? Does anyone have the results? 18.6. Okay, so the gain, using this equation, what is AF? It's 20. What is the frequency that we have? 500K over 200K kilohertz. Square root of 1 plus F is again 500 for 200K. And what was the result that you got? This is in a power of 2, by the way. Okay, it's 18. 18.6. Let me double check that. I think it should be a little lower, or maybe this is right, so. Yes, 18.4. Yes, 18.6. So I can see this is lower than the maximum gain because now we are in the stop region. Oh, God. So now we are in the stop region. So the gain is going to be around here, 18. Okay, I think that's it for today. Thank you so much. And I'll post an announcement about the final exam and the next exam on. Have a great weekend.